Okay, hi. So I'm Nicola. This is a joint work with Dominic, who's there. And this is a talk about data compression. Okay, so what is text compression? So it's so a compressor, a lossless compressor, is a function, an injective function, that goes from strings from some alphabet sigma to bit strings, such that the bit size of the compressed representation of our text is as close as possible. I mean, the bit size is as close as possible to the information content of the text. So what is the information content? So we know how to do that, how to measure the information content of a string. This is the Kolmogorov complexity, so the size of the smallest program that generates T. But the problem is that this is not non-computable. So this is a non-computable function, so we cannot hope to get an optimal compressor. We cannot compress optimally. So we must use heuristics to compress, some heuristic algorithms. So an example of such an heuristic is entropy compression. This dates back to Shannon. Basically, we want to assign a bit code to every character in our string so that we assign less bits to more frequent characters. Okay, so we minimize the bit size of the final encoding. Unfortunately, this works well when we have a source and we know the probabilities of characters, a memoryless source. But the problem is that with the repetitive strings, this fails. So if we have a source with memory, with long memory, so for example, we have a text that's so a repetition of t time of the same text, so the text t repeated t times, then we have that entropy, so the entropy h t to the t, the entropy of this text is basically t times the entropy of the main text, the text t. While it's easy to see that the Kolmogorov complexity is able to capture this t repetition. So basically, you simply write the program for t, and then you add an instruction which says repeat for t times. Okay, so basically, with entropy, we get a t blow up, while it's only a log t additive blow up is necessary. So we need better heuristics in order to capture repetitiveness. And here, dictionary compressors are coming into play. So what is a dictionary compressor? So it's a representation of a string as a concatenation of elements, so strings from some dictionary, so from set of strings. So probably you all know about this. So Lempel-Ziv 77 is an example of dictionary compressor. So in this algorithm, basically we scan the string left to right. And then we find so we break the string into phrases, and each phrase is the longest phrase that appears before, the longest substring that appears before. So for example, okay, here we have the first occurrences of BA, then we have B, because B appears before, but BB does not appear before, then BAB, because BAB appears before, and so on. And then we encode every phrase as a pointer to the previous occurrence. So Lempel-Ziv 77 captures extremely well repetitions, and it can compress thousands of times better than entropy compression, also in practice. So this is super good for repetitive texts. So since the 70s, we've developed a lot of different dictionary compressors, which all capture in some way repetitions. So we have the Barosule transform, which is a text permutation, which has long runs of the same character if the text is repetitive, and then you just run length compress it. We have macro schemes, which are basically like Lempel-Ziv 77, but they are bidirectional, so we can copy also from forward. Grammars, so the smallest grammar that generates only the text, college system, word graphs, and so on. So we have a lot of different dictionary compressors. So they are very good at capturing repetitiveness, but we have this unsatisfying situation. So first of all, we have a large number of apparently unrelated compression techniques, which basically are solving the same problem. So they are capturing repetitions. And for each compressor, we developed a lot of different solutions to solve particular problems. So for example, the random access problem. So this is the compressed computation domain. So we want to solve some problems in compressed space. So for example, random access, I give you a compressed representation of the text, and you want to access the ith letter in the text in compressed space. So for each of these compressors, many different solutions have been developed. And we have one more problem: what is string repetitiveness? So it's not even clear what is a repetitive string, how to measure repetitiveness. So here we try to answer all these questions in this paper, and we introduce this new object, string attractors. So our idea is to try to capture all distinct substrings in the text using few positions. So basically, we define a string attractor to be a subset of the text positions, so that every substring of the text has an occurrence that crosses a position in your set. Okay, so here we have an example. So this is a string, and we for example, this is a string attractor, so these 4 positions. Because if you look at every substring, so for example, ABC, so here does not cross any position, but there's another occurrence that crosses one of these positions, okay? So CC is another example. We have an occurrence here of CC, which crosses one of our positions. So this is an attractor of size 4. So why are these objects interesting? So our first result is that compressors are basically attractors. So our first theorem says that if you're given a compressor, one of the dictionary compressors I showed you before, then each of these compressors generate a string attractor of the same size of its output. So for example, if you take Lempel-Ziv, you can, here we have the example. For Lempel-Ziv, it's quite easy. So you you build your factorization, and then you pick the first position of every phrase. And you can prove that this is a string attractor. This is easy, and for other compressors, it's a bit more hard and surprising. For example, for the Barzouillet transform, it's not that easy to prove, but it's quite surprising that this is possible. Then our second result is that surprisingly also the other direction holds. So if we are given an attractor, then we can build a compressor. What does this mean? So this means that if we are given a string T and a string attractor for the string of size gamma, then we can build a macro scheme. So this, I remind you, is a bidirectional Lempel-Ziv. A macro scheme of size gamma log n over gamma. We can build a collage system, which is a more powerful grammar, basically, of the same size. Or we can build a grammar of size gamma log squared n over gamma. So we can go also in the other direction. So here's an example. How do we get a macro scheme? So a bidirectional Lempel-Ziv. So consider this example. So this is a text. I didn't write characters for simplicity. And let's suppose that this is an attractor of size 2 for this text. Okay, so this position and this position. So the construction of this macro scheme, it's a factorization of the text, is the following. Basically, you build phrases, exponentially increasing phrases from the attractor positions. So length 1, length 2, length 4, length 8. So first you build the phrases, and then you have to show how to choose the sources. So for the sources, you basically, for each phrase, like this red phrase, as a source, you pick any occurrence that crosses an attractor. So this occurrence exists by definition of attractor. So just pick one of these occurrences, and do this for every phrase. And then it's sufficient to note that if you are inside of a phrase of length 2 to the e, then the source overlaps only phrases of length at most 2 to the e minus 1. So you have, you can basically, you can extract characters like this. So if you have a macro scheme of this kind, basically to extract a character, basically so this green character, for example, you identify its phrase, and then you follow the source of the phrase, and you end up here. And you note that this phrase has length at most half of the size of this phrase. And you repeat recursively until you fall on one of the attractor positions. And so that's also why we chose this name. So as you can see in this example, the position is being attracted by the attractor. So you get exponentially closer at each step. OK, and the size of the macro scheme you get in the end is gamma log n. And you can easily improve to gamma log n over gamma. OK, but more surprisingly, we can build optimal data structures based on string attractors. So we use basically the same reduction I showed you before for macro schemes. And it's just sufficient to note that this was a random access data structure, because just following these sources, you can extract each character. So this is another theorem we get. So given an attractor of size gamma, we can build a data structure of size gamma polylog n that can extract any character in this time here, log n over log n. And surprisingly, this is optimal. So this is a theorem from 2013, and this was proved for grammars. But and we adapted their proof. It's easy to adapt to our case, and this shows that this structure is optimal. You can't do better than this in this space here. And not only, but by the reduction we have compressors to attractors, we have also that our data structure can, works for any compressor. So this is the first universal data structure that works for every dictionary compressor. So before we had a different solution for every of these compressors. Now we have a single solution which is also optimal. And we can prove that the solution is indeed optimal also for most of the compressors, so for Lempel-Ziv, grammars, and so on. We also get some other interesting results. So note that we proved the bidirectional reduction. So we went from attractors to compressors and the other way around. And so this allows us to uncover, first of all, the approximation ratio of compressors with respect to the smallest attractor. So you can actually prove that dictionary compressors are approximation algorithms for the smallest attractor. And the approximation ratios are typically polylogarithmic. And then we get, surprisingly, we get a new technique to get new relations between dictionary compressor sizes. Yes. So for example, we can prove that the size of Lempel-Ziv 77 is always bounded by the size of the rank length Barzile transform, which is another compressor, times log square n. And this was not known before. And we get many other relations of this kind here. Then, computational complexity. So now it's interesting to study the computational complexity of finding the smallest attractors, since these objects are so interesting. So what's the complexity of this problem? So first of all, we generalize the notion, and we define a string k attractor. So a k attractor is basically you want to capture strings of length at most k. So it's the same as before, but just strings of length at most k. And the attractor problem is basically the n attractor problem. Okay. So what we prove is that k attractor is NP complete for k greater than or equal to 3. And it's easy to observe that one attractor is linear time. This is trivial. And this is a super exciting open problem. What's the complexity of two attractors? We weren't able to solve this. This seems a super easy problem, but it's not easy. So find out the smallest set of positions that capture all substrings of length at most 2. So 1 or 2. This is hard. We don't know the complexity of this problem. So for the NP completeness, I can give a sketch. Basically, it's a reduction from set cover, sharp 3 set cover. So you have, this is the family of sets, Ci, and this is the universe. And then the idea is to represent, so to build a string. And in our string, we have a different substring for every subset, Ci. And the idea is that so every element, for example, A1 becomes A11, A12, A13. So these are alphabet characters, okay? So we build this string here. We also have some additional characters, $, hash. And then we will concatenate all these strings together. Then we introduce some other strings. There are a lot of details, but now I have to skip them. So that so these strings will force any attractor to cover for free these substrings for so hash or hash, or all substrings of A2, A3 for every element of the universe, and all substrings of this. And basically, the main observation is then that choosing a set from the set cover instance is equivalent to make one of these choices here. So basically, we are left to cover only these substrings here. And the observation is that we need to cover this substring here, AJ1, 2, and 3, only if this is not covered in some other string corresponding to some other set. And basically, the observation is that then there are only basically two possible choices of size, in this case, 8 and 7. So, so the attractor positions are the orange positions here. So the choice of size 8 corresponds to choosing the set. And as you note, we cover our substrings A11, A12, A13. So all elements in the set are covered. The other choice has size 7, so one less, and does not cover the elements in the set, which means that this is equivalent of to choose or not choose the set from the set cover instance. Then we get a lot of other reductions. So from reductions from k-vertex cover to k-set cover, we can show the APX hardness of the the K attractor problem. So we show that for any constant K larger than 3, minimum K attractor is APX complete. And then we derive even some constants using some known results. We show that below some constant, so this is ridiculously close to 1, below this constant is NP-hard to approximate the minimum K attractor, okay, within this constant. And we also obtain better, good approximations using approximation algorithms for set cover, for K set cover. And for example, for 3 attractor, which is NP complete, we get a 1.95 approximation. Okay, so that's all the open problems. So there are a lot of super nice open problems. So better approximation bounds. Can we approximate, for example, 3 attractor better than 1.95? And complexity of 2 attractor. This is an open problem. This is also a nice open problem. Can we compress in gamma space? So we show that it's possible in gamma log n over gamma, but we don't actually know if it's possible to compress in gamma space. And then, finding more universal data structures. We have been doing some work also in this direction here. Okay, that's all. Thanks. Yes.
Did you guys try any approximation algorithm for 2 attractors?
No, yes, so we have 2 approximation, which is super easy. And I think we can, Dominic, can we get a log 2 approximation with a set cover thing? Maybe, yeah, we can even get a log 2 approximation, I'm not sure. But so the problem, the interesting thing is that there is actually polynomial time if you want to capture only substrings of length 2, exactly 2. When you introduce also substrings of length 1, so 1 and 2, then it's hard to solve it. Yes.
Are there any concrete compression techniques that cannot be explained in?
We don't know of other techniques. Basically, we looked into all known dictionary compression techniques, which are these ones here, and we proved the reductions, but we are not aware of. We have our conjecture is that any compressor that is able to exploit repetitiveness then must induce in some way a string attractor of the same size. But this is just a conjecture. It's not easy to. Yeah. Yes.
Do you think this line of research will eventually produce new compression algorithms?
Yeah, this would be nice. Yeah, this is related to this open problem here. So if we find a way to compress in gamma space, then yes, because so gamma can be much smaller than the outputs. The minimum gamma. So the size of the smallest attractor is much smaller than the size of any compressor we know of. So if we can prove that we are able to compress in this space, then we can get new compressors, much powerful compressors also. Yes.
Thank you.
Thanks.